Deep within the boundaries of Yellowstone National Park, a landscape quietly respires. Pine trees anchor themselves into soil that refuses to rest, while geothermal pools shimmer with brilliant colors painted by heat-loving microorganisms. Visitors walk along wooden boardwalks, admiring sudden, rhythmic eruptions of water and steam cutting through the crisp mountain air. Look closer at the ground beneath these walkways, however, and a much more profound rhythm reveals itself. Satellites positioned miles above the planet track microscopic shifts in the terrain, recording changes invisible to human eyes. Millimeter by millimeter, the caldera floor rises toward the sky. Months later, the terrain might subside, only to swell again in a silent, planetary respiration. We stand upon a living surface, one expanding and contracting with the slow deliberation of a buried lung. Recognizing this subtle movement requires a leap of imagination, aided by brilliant modern instrumentation. Geologists have scattered sensitive GPS receivers across the park, creating a digital nervous system designed to monitor every tremor. Through telemetry and rigorous mathematical analysis, our species has deciphered the silent language spoken by the ground. Scientists watch data stream into laboratories, witnessing solid rock behave like a flexible membrane. Such observations dismantle our intuitive understanding of the world. Everyday experience teaches us that rock is absolute, a universal symbol of permanence and unyielding strength. Yet, the numbers flooding our screens prove unequivocally that the terrain we consider eternal is actually in constant, fluid motion. Beneath the soil and bedrock lies a sleeping architecture, hidden just below the floorboards of our everyday reality. Think of the continents not as fixed, immutable foundations, but as a temporary mosaic resting upon a restless interior. Humanity builds towering cities, traces extensive highways across flat plains, and erects large monuments with an implicit trust in the structural integrity of the earth. Geology, however, tells a radically different story. Down in the absolute darkness, where sunlight has never penetrated, monumental columns of molten material ascend. Rivers of magma branch out into subterranean chambers, forming a labyrinthine structure rivaling the complexity of any metropolis we have ever engineered. This hidden framework supports everything we know, continuously shifting, relentlessly exchanging thermal energy with the cold void of space above. Before journeying deeper into these concealed corridors, take a moment to mirror the landscape surrounding you. Draw in a slow, deliberate breath, expanding your lungs just as the caldera floor swells with subterranean heat, and then release it. As you find your center in this steady rhythm, consider joining us permanently on this expedition of the mind. A subscription to this channel allows you to step beyond the superficial layer of everyday perception and dive into the mechanics governing our universe. Every interaction builds a community dedicated to the pursuit of knowledge, honoring the relentless curiosity defining humanity. Together, we can peel back the layers of reality, examining the raw, untamed forces shaping our existence. Returning to the ground beneath our feet, we must dismantle the most persistent myth of human experience. Solid Earth is an illusion confined to our immediate, localized perspective. To comprehend the true nature of our planet, one must zoom out conceptually and observe the globe in its entirety. The crust we inhabit, complete with towering mountain ranges and abyssal ocean trenches, represents a delicate outer shell. Imagine our whole world reduced to the physical size of a common apple. That rigid exterior we inhabit, encompassing all our oceans and land masses, would be substantially thinner than the fruit's fragile skin. Floating beneath this delicate boundary is the mantle, an expanse of silicate rock subjected to such extreme temperatures and pressures that it defies our everyday understanding of solid matter. Rock at these extreme depths behaves unlike anything encountered on the surface. Driven by primordial heat left over from the solar system's violent formation and the steady decay of radioactive isotopes, the deep interior churns in a slow, viscous dance. It flows with the consistency of warm glass over millions of years. Massive convection currents rise from the boundary of the outer core, carrying vast thermal energy upward before cooling and sinking back into the abyss. We cannot witness this heat engine directly. Instead, human intellect has developed an array of tools to visualize the invisible. Scientists construct intricate three-dimensional maps of the deep interior by reading subtle variations in seismic waves generated by distant earthquakes. We have effectively turned the globe into its own diagnostic machine, utilizing physics to peer through thousands of kilometers of solid rock. The mapping of this dynamic interior reframes our relationship with the ground itself. Yellowstone is not merely a pristine sanctuary for wildlife. It serves as a transparent window into the planetary engine. The thermal energy warming those bubbling mud pots and launching geysers into the sky originates from a gigantic mantle plume, a towering pillar of superheated rock rising all the way from the core mantle boundary. As this ascending column encounters the base of the North American tectonic plate, it melts the surrounding crust, pooling into a sprawling reservoir of magma. This subterranean lake acts as a pressure vessel, quietly accumulating energy over tens of thousands of years. It does not harbor malice, nor does it actively seek destruction. It obeys fundamental laws of thermodynamics, seeking equilibrium in a universe defined by energy's constant transfer. Consider the sheer cognitive triumph required to map a structure we can never physically touch. The magma chamber beneath Wyoming spans dozens of kilometers, a reservoir of liquid fire entombed within absolute darkness. Generations of geophysicists spent decades refining their instruments, listening patiently to the echoes of distant tremors ringing through the planet. Every earthquake, no matter where it occurs, sends acoustic waves traveling through the core and mantle. As these waves pass through different materials, they change speed, bending and refracting just like light passing through a glass prism. Supercomputers piece together the density and temperature of the rock miles below by capturing these altered waves at the surface. Humanity has essentially learned to see with sound, illuminating the darkest reaches of our world through the power of mathematics and deductive reasoning. This intellectual victory allows us to appreciate the delicate balance maintaining our everyday reality. The ground beneath us feels solid only because our lifespans are brief compared to the vast stretches of deep time. We exist in a fleeting moment, a tiny sliver of observation amidst a geological epoch spanning millions of years. When viewed through the lens of planetary time, the rigid crust loses its permanence. Continents drift across the globe like rafts on a sluggish river, colliding to form towering peaks and tearing apart to birth new oceans. The surface we call home acts as a transient, cooling boundary, separating the fiery chaos of the interior from the freezing vacuum of space. This vast geological time frame reveals another astonishing mechanism at play. Continents do not simply rest atop the mantle, they literally float. Much like large icebergs drifting through an Arctic sea, the thick, buoyant landmasses we call home displace the denser, semi-fluid rock below. Mountain ranges possess deep, invisible roots plunging far into the lithosphere, maintaining a delicate gravitational balance. When ancient glaciers melt or tectonic forces erode a towering peak, the land subtly rebounds, rising higher out of the mantle. The principle of isostasy demonstrates that the earth beneath our feet behaves far more like a slow-moving ocean than a rigid floor, seeking equilibrium in a dynamic, ever-changing system. Such a continuous cycle of creation and deformation alters how we perceive a place like Yellowstone. Those towering geysers are not merely tourist attractions. They act as vital pressure relief valves for a system of unimaginable scale. Water seeps down through fissures in the fractured rock, journeying miles into the dark until encountering sections of the crust superheated by the magma below. Flash boiling instantly, the liquid expands, rushing back toward the surface in a spectacular display of physics. Each eruption serves as a compelling reminder of the vast thermal disparity driving the evolution of our planet. The terrain above remains serene, carpeted in green pine forests and wandering herds of bison, masking the huge forces operating just out of sight. Maintaining this serene facade requires a delicate structural equilibrium within the rock itself. Overlying crust pushes down, attempting to contain the expanding, buoyant magma ascending from the depths. A continuous, silent negotiation occurs between the structural integrity of the stone and the mounting pressure of the liquid fire. As long as the rock holds, the landscape breathes peacefully, rising and falling by mere millimeters. Yet, the energy flowing from the core remains constant, feeding the underground reservoirs without pause. The sleeping architecture beneath the floorboards continues to grow, expanding its chambers and reinforcing its molten columns. We stand above this complex machinery, armed with the knowledge to comprehend its workings, marveling at the quiet, ominous potential locked away in the dark. To fully grasp what lies hidden within the earth, one must discard the classic silhouette of a volcano. Generations of artists and storytellers have trained our minds to visualize volcanic peaks as majestic, solitary cones piercing the clouds. Mountains like Fuji or Kilimanjaro dominate their landscapes, built gradually through countless localized eruptions, stacking layers of ash and hardened lava over eons. We effortlessly map these towering summits, their steep flanks offering a clear visual warning of their fiery nature. Calderas, however, defy this familiar geometry. Instead of presenting a towering peak, they manifest as a deep physical absence. Massive depressions scarred into the topography, stretching for tens of miles, mark the locations where solid ground vanished. It takes deep geological insight to recognize these sunken basins rather than merely looking upward toward the sky. Gazing across a large volcanic depression, you are not viewing a mountain that has yet to erupt, but rather looking directly into the collapsed roof of an ancient subterranean void. Far beneath this sunken topography operates a thermodynamic engine of staggering proportions. Deep within the mantle, localized anomalies generate columns of abnormally hot rock ascending toward the crust. Geologists track these vast thermal upwellings using advanced seismic tomography, observing how they pierce through cooler surrounding layers like slow-moving thermal drills. Reaching the rigid lithosphere, this rising heat encounters an impenetrable barrier of thick continental bedrock. Thermal energy has nowhere to go but outward and upward, transferring immense temperatures directly into the tectonic plate above. Solid crust begins to melt under this sustained assault, slowly transforming the rigid foundation of the continent into a swirling pool of liquid rock. Unlike the fluid basalts erupting continuously in places like Hawaii, melting continental rock creates a different chemical mixture. High concentrations of silica form complex tetrahedrons that link together in the dark, forging expansive, three-dimensional molecular webs that alter the behavior of the newly formed liquid. Viscosity becomes the defining characteristic of this subterranean reservoir. Rich in minerals like quartz and feldspar, the resulting rhyolitic magma behaves more like a dense, unyielding paste than a free-flowing fluid. Gases continuously dissolving into this viscous mixture struggle to escape. Water vapor, carbon dioxide, and sulfur dioxide become trapped within the interlocking silica polymers, unable to bubble toward the surface. Dissolved volatiles require massive amounts of room to expand, yet they remain confined by the heavy weight of the overlying rock. Physics dictates that temperature, volume, and pressure must maintain a proportional relationship within any closed system. Adding continuous heat from the mantle plume below forces the internal pressure of the chamber to climb steadily. Centuries bleed into millennia, while this localized pocket of extreme thermodynamic stress quietly builds beneath the forest floor. Above this expanding reservoir, the lithosphere acts as a gigantic containment dome, millions of tons of solid rock pressed downward, relying on fundamental principles of structural mechanics to keep the highly pressurized liquid below in check. Materials science teaches us about elasticity and tensile strength, crucial parameters defining how much upward force the crust can endure before fracturing. Bedrock, despite its seemingly rigid nature, possesses a measurable capacity to bend. Sedimentary and igneous layers stretch across vast distances, warping upward to accommodate the swelling chamber beneath them without snapping. Strain accumulates slowly within the crystalline lattice of the rock overhead. Satellites orbiting our planet document this deformation, beaming back high-resolution radar data that allows human minds to calculate the tension accumulating in the bedrock. Surveyors note subtle changes in elevation, streams altering their natural courses by fractions of a degree, and ground surfaces tilting at imperceptible angles. All these microscopic alterations tell a mathematical story of upward stress approaching the material limits of the Earth. This mechanical limit frames the true nature of a supervolcano. We are not dealing with a localized vent periodically releasing gentle streams of steam and lava to relieve tension. We are examining an inevitable structural failure on a continental scale. Every solid material possesses an ultimate breaking point. Engineers designing steel bridges calculate shear stress to ensure their structures withstand heavy, dynamic loads. Geologists apply these same engineering principles to the planetary crust. A large dome capping the magma chamber stretches thinner and thinner as the volume of trapped gas and liquid continues to expand. Microfractures propagate silently through the bedrock, severing the molecular bonds that hold the landscape together. Seismometers detect these tiny snaps as swarms of low-magnitude earthquakes, a harmonic tremor signaling that the containment vessel is weakening under the strain. To visualize this hidden geometry, we must step away from traditional geology and embrace the perspective of structural engineering. A magma chamber fueling a supervolcano is rarely a single, spherical cavern waiting to burst. Seismic imaging reveals an intricate, branching network of sills and dikes, horizontal sheets of molten material pushing their way through weak points in the crust. Slowly, these independent pockets of magma merge. Over tens of thousands of years, they coalesce into a continuous, shallow reservoir encompassing thousands of cubic kilometers. The heavy roof supporting the surface ecosystem rests precariously on this liquid foundation. As long as the pressure below equals the immense weight above, the landscape remains stable. Thermodynamics, however, allows no permanent equilibrium here. Heat from the Earth's deep interior continuously feeds the system, acting as an unstoppable conveyor belt of thermal energy, ensuring the internal pressure only moves in one ascending direction. Operating as a purely mechanical ticking time bomb, the caldera waits for a structural failure to release its stored energy. Herein lies the awe-inspiring reality discovered by human science. We have decoded the mechanisms governing these colossal systems, transforming an invisible underground phenomenon into a mapped, quantifiable process. Researchers calculate the temperature necessary to liquefy continental crust by studying ancient rocks. Laboratory experiments compress mineral samples inside diamond anvils to recreate the conditions found 20 miles underground. Through these rigorous empirical methods, our species has isolated the core variables controlling a planetary-scale detonation. We know with absolute certainty that the tipping point arrives not from a sudden spark or a magical trigger, but from a simple, overwhelming mechanical deficit. When the upward pressure of the expanding trapped gas exceeds the tensile strength of the overlying rock by a single fraction of a unit, the dome will inevitably fracture. Fracturing the rocky roof represents the primary catalyst for a fascinating chain reaction. A crack propagating all the way to the surface immediately depressurizes the magma chamber below. Similar to popping the sealed cap on a vigorously shaken carbonated beverage, the sudden drop in pressure causes the dissolved gases to exsolve and expand. Trillions of microscopic bubbles form instantaneously within the viscous rhyolite. Expanding gases tear the liquid magma apart from the inside out, shattering it into jagged shards of glass and pulverized rock known as volcanic ash. This rapid volumetric expansion cannot possibly be contained by any natural structure. Structural failure of the roof thus initiates an explosive decompression, instantly transforming a pressurized liquid into a supersonic combination of gas and solid debris capable of evacuating thousands of cubic kilometers in a matter of days. Ejecting such a volume of magma permanently removes the physical foundation, supporting the surface above. Deprived of its underlying support, the fractured crust collapses inward, creating the sunken caldera that constantly confounds our traditional image of a conical volcano. Instead of viewing this mechanism with despair or terror, we must recognize the sublime power of the natural world and our ability to comprehend it. Early humans surely gazed upon volcanic landscapes with profound confusion, attributing fiery eruptions to the wrath of capricious deities or supernatural forces. Modern humanity has systematically replaced that primal fear with deep analytical understanding. We measure the isotopic signatures trapped in microscopic quartz crystals to read the complex thermal history of past eruptions. Mass spectrometers decode the chemical evolution of magma chambers, detailing how molten rock cools, crystallizes, and reheats over 100s of millennia. Armed with advanced mathematics, rigorous chemistry, and quantum physics, we stand confidently atop these slumbering giants, not as helpless victims, but as enlightened observers capable of reading the very heartbeat of the planet. Such scientific grounding reveals that the accumulation of geothermal energy is a silent, methodical process. Nature does not provide a dramatic, flashing countdown to announce its intention. Physical laws governing stress and strain operate without fanfare. Fault lines slip, rock layers flex, and thermal gradients steepen in absolute darkness, far removed from human observation. To the unaided eye, a supervolcano on the verge of structural failure looks like a tranquil, thriving wilderness. Forests continue to grow robustly above the flexing dome, wildlife grazes peacefully on the swelling plains, and crystal-clear rivers flow over rocks experiencing immense subterranean tension. Only through the powerful lens of human ingenuity, through the vast deployment of our orbital satellites and embedded seismic arrays, does the true magnitude of the situation become apparent. The physics of this process forces us to confront the sheer scale involved in planetary mechanics. A standard volcanic eruption might eject 1 or 2 cubic kilometers of material, enough to alter a local landscape and temporarily disrupt regional weather patterns for a few weeks. Supervolcanoes operate on an entirely different order of magnitude, demanding a radical shift in how we quantify geological events. Mathematical formulas governing these massive magma chambers dictate that when structural failure occurs, the volume of evacuated rock routinely exceeds 1,000 cubic kilometers. Immense output on this scale transitions the event from a localized geological hazard into a complex continent-altering phenomenon. Energy released during these structural collapses rivals the immense kinetic impact of major celestial bodies striking the Earth. Yet, this incredible power originates from within, serving as a natural, unavoidable byproduct of a cooling planet managing its vast internal thermal budget. To track the history of these massive structural failures, we must decipher the subtle clues left behind in the global rock record. Ancient ash beds scattered widely across entire continents provide a physical, durable footprint of past cataclysms. Geochemists analyze these deeply compacted layers of glass and pulverized minerals, tracing their unique chemical signatures backward through time to specific caldera collapses. Forensic geology proves conclusively that the Earth has repeatedly built and destroyed these massive subterranean reservoirs throughout its long history. It remains a recurring planetary mechanism, operating on a timescale so vast it effortlessly dwarfs the entirety of recorded human history. While we chart these ancient ash beds to understand the physical history of our planet, another, far more intimate record unexpectedly carries the profound echoes of a prehistoric structural failure. Geological timelines naturally align with a surprising biological mystery hidden deep within our own cellular structure. The stratified layers of Earth provide only one half of the story. The other compelling narrative is revealed in the molecular code of human ancestry. Before examining the fallout of a modern caldera collapse, we must first look backward to a time when our nascent species encountered this immense planetary machinery head-on. Silent subterranean pressure eventually intersected with the fragile journey of early humanity, leaving an indelible genetic mark that scientists have only recently managed to decode. Decoding this molecular history rewrites the traditional narrative long taught in anthropology classrooms. For decades, mainstream academic thought presented a linear, straightforward progression of human expansion. Textbooks illustrated a steady march originating from the African savanna, where early hominids mastered bipedalism and gradually dispersed across adjacent continents. Researchers confidently mapped a continuous upward trajectory regarding population numbers, assuming a constant rate of reproduction and steady territorial conquest. Scientists believed our ancestors simply multiplied generation after generation, slowly filling every ecological niche available on the globe. The fossil record made logical sense through this classical lens prior to the genomic revolution. Archaeologists unearthing stone tools in disparate geographical regions assumed these artifacts belonged to ever-growing tribes, steadily pushing outward into uncharted territories. Uninterrupted progress served as the guiding philosophy. Migrating bands encountered new climates, adapted their hunting strategies, and flourished without experiencing any catastrophic, species-wide interruptions. Linear models offered a comforting, easily digestible version of evolutionary history, one characterized by unstoppable biological momentum and predictable growth. Transforming our understanding required a technological leap far beyond unearthing physical bones. Modern geneticists, armed with unparalleled computational power, began reading the intricate biological code embedded within our very cells. Sequencing human DNA opened an entirely new investigative frontier, independent of the fragmentary fossil record. Biologists essentially became molecular historians, utilizing algorithms to trace the lineage of specific genes backward through the millennia. We developed the extraordinary capacity to reconstruct ancestral family trees, utilizing nothing more than drops of blood and swabs of saliva collected from contemporary populations around the world. These lineages rely upon elegant biological mechanics. Mutations occur within our DNA at predictable intervals, functioning as remarkably precise chronological markers. Certain segments of our genome, specifically mitochondrial DNA passed from mothers and the Y chromosome inherited solely from fathers, provide uncontaminated chemical trails. Mathematicians calculate exactly how long ago these distinct groups shared a common ancestor by counting the microscopic alterations differentiating modern populations. Mastering this molecular timekeeping stands as a towering achievement of human intellect, granting us the ability to peer deeply into a prehistoric era long before the invention of written language. This vast dataset shattered the long-held assumption of uninterrupted human proliferation. When supercomputers finalized their complex genomic comparisons, the resulting evolutionary tree lacked the broad, expansive base expected from a continuously growing population. Instead, the digital models revealed a stark, undeniably abrupt anomaly. Genetic variation among all living humans today is impoverished when compared to the vast diversity found in other primate species. Our DNA is unusually uniform, a puzzling characteristic that contradicts older theories regarding a slowly diversifying global population spanning hundreds of thousands of years. Confronting this lack of diversity led researchers to a mathematically undeniable conclusion. At some point in our ancient past, the vast array of human genetic traits was severely truncated. Evolutionary biologists refer to this phenomenon as a population bottleneck, a critical phase where external pressures drastically reduce the total number of breeding individuals. Imagine a very wide river suddenly forced through a remarkably narrow rocky gorge, restricting the volume of water permitted to pass downstream. Only a fraction of the original genetic material survived this restrictive passage, meaning every human being alive today descends from an astonishingly small pool of resilient survivors. The triangulation of this genomic constriction required immense analytical rigor. Independent laboratories cross-referencing thousands of individual DNA samples consistently arrived at an identical chronological window. Roughly 74,000 years ago, human genetic drift experienced a profound reset. Mathematical models demonstrate that during this specific epoch, our global population numbers plummeted rapidly. Statistical estimates vary, but credible simulations suggest the total breeding population of our species dropped to merely a few thousand individuals scattered across a changing landscape. A demographic contraction of this severity placed our lineage on the precipice of elimination. Yet, rather than viewing this era as a bleak tragedy, we must recognize it as the ultimate crucible of human ingenuity. Those remaining bands of early humans did not survive through passive luck. They endured through extraordinary cognitive adaptation. Enduring extreme environmental stress required our ancestors to leverage their unique intellectual capacities to the absolute maximum. They forged tighter social bonds, developed innovative survival strategies, and relied upon complex communication to share vital resources. This genetic pinch point effectively filtered our species for resilience, ensuring only the most cooperative and adaptable traits propagated forward into modern humanity. The archaeological sites corresponding with this chronological marker reveal a fascinating cultural acceleration. Far from regressing into a primitive state, artifacts left behind by these survivors showcase an explosion of behavioral modernity. Stone blades became sharper and more refined. Evidence of long-distance trade networks began to emerge, suggesting isolated groups realized the necessity of mutual support to outlast harsh conditions. Symbolic thinking, evidenced by early forms of artistic expression and bodily adornment, flourished when existence became most demanding. Intense pressure did not break the human spirit. It catalyzed an unprecedented intellectual awakening. Recognizing how humanity triumphed over this extreme hurdle prompts a far larger scientific inquiry. Biologists diagnosed the demographic crash, but the identification of the global catalyst required expanding the investigation across multiple scientific disciplines. Localized droughts or regional conflicts simply cannot account for a simultaneous population collapse affecting multiple, widely separated continents. Contagious diseases might devastate specific territories, but vast oceans and impenetrable deserts naturally quarantined prehistoric populations from global pandemics. An anomaly of this unique scale demanded an environmental shock capable of enveloping the entire planet simultaneously. Searching for an environmental disruption matching the magnitude of the biological data led investigators directly to the polar ice caps. Climatologists drilling deep into ancient glaciers extract long cylinders of frozen history, where trapped air bubbles and isotopic ratios record temperatures from the prehistoric atmosphere. Analyzing ice cores from 74 millennia ago revealed a staggering climatological shift. Planetary temperatures plummeted abruptly, initiating a severe global freeze lasting for several brutal years, followed by decades of unstable weather patterns. Molecular markers hidden inside our cells and atmospheric records frozen beneath the poles aligned in undeniable unison. Connecting a sudden global deep freeze to a dramatic loss in genetic diversity, solved two major pieces of the puzzle, yet the ultimate trigger remained elusive. Changes in solar radiation or gradual orbital shifts occur far too slowly to cause such an instantaneous atmospheric cooling. Meteorological models indicated that plunging the Earth into an immediate freeze required injecting massive quantities of sunlight-blocking material directly into the upper stratosphere. The source of this sudden aerosol injection meant returning our focus back to the solid ground. Our ancestors experiencing this dramatic near erasure were not targeted by microscopic pathogens or cosmic fluctuations, but rather by the exact subterranean mechanics we previously mapped. Following the trail of evidence downward forces an integration of evolutionary biology and deep Earth geophysics. Somewhere on the globe, a localized zone of extreme thermodynamic stress successfully breached its containment dome at the wrong moment for a flourishing prehistoric humanity. We must now merge the microscopic language of DNA with the macroscopic violence of tectonic plate dynamics. To identify this large structural collapse, we must look toward a specific geographical coordinate, an island landscape where the Earth abruptly shattered its own surface to release millions of years of pent-up thermal energy. Deep beneath the tropical archipelago of Indonesia, an unstoppable tectonic collision drives one of the most dynamic geological engines on Earth. Here, the dense, oceanic crust of the Indo-Australian plate plunges relentlessly downward into the mantle beneath the lighter Eurasian landmass. Grinding rock generates immense friction along this subduction zone, dragging seawater deep into the Earth's superheated interior. Introducing water into the pressurized mantle drastically lowers the melting point of the surrounding rock, triggering a process known as flux melting. Immense volumes of buoyant magma generate continuously along this subterranean boundary, rising upward to pool within the continental crust of Sumatra. Over millions of years, this localized thermal anomaly engineered a massively large reservoir of liquid rock, setting the stage for an event that would alter the trajectory of our species. We must stretch our geographical imagination to quantify the sheer volume of this hidden Sumatran chamber. We are not describing a modest pocket of lava preparing to build a standard mountain. Far below the equatorial forests, an ocean of viscous, gas-rich, rhyolitic magma expanded until it spanned over 100 kilometers in length. Millennia passed while dissolved volatiles strained against the crystalline lattice of the overlying bedrock. Slowly, the structural integrity of the lithosphere reached its breaking point. 74,000 years ago, the rocky containment dome stretching across the region finally fractured, depressurizing the vast subterranean sea of liquid fire. Catastrophic decompression instantly tore the magma apart from the inside out. Trillions of expanding gas bubbles shattered the highly pressurized liquid into microscopic shards of pulverized glass and razor-sharp rock. Thrust upward by huge thermodynamic force, an eruptive column punched directly through the troposphere, accelerating at supersonic speeds until it breached the stratosphere. Volcanologists classify this staggering detonation as a magnitude 8 event on the Volcanic Explosivity Index, the highest possible ranking for a geological explosion. Upwards of 2,800 cubic kilometers of solid earth evacuated the chamber in a matter of days. To visualize this quantity, one must imagine a solid block of stone covering the island of Manhattan and extending straight upward into the sky for over 40 miles. Displacing such a huge amount of material left a gaping void within the crust, causing the regional landscape to collapse inward and form the breathtaking depression known today as Lake Toba. Yet, the true legacy of this detonation did not remain confined to the Indonesian archipelago. High-altitude stratospheric winds intercepted the rising column of pulverized glass and sulfur dioxide, transforming a localized structural failure into a hemispheric phenomenon. Strong atmospheric currents grabbed the billions of tons of suspended debris, quickly distributing the thick tephra cloud westward across the Indian Ocean. Vast swaths of the Asian continent, extending all the way into the heart of the Indian subcontinent and reaching the eastern shores of Africa, found themselves blanketed beneath a heavy, suffocating layer of pale volcanic fallout. Geologists refer to this widespread blanket of debris as the youngest Toba tuff, a remarkably durable geological fingerprint etched into the planet. The discovery of this specific ash layer today involves analytical chemistry and meticulous excavation. Field researchers retrieve deep-sea sediment cores from the Bay of Bengal and unearth compacted soil samples from ancient riverbeds in central India. Embedded within these distant samples are cryptotephra, microscopic glass shards carrying the chemical signature of the Sumatran magma chamber. Subjecting these microscopic fragments to rigorous argon-argon radiometric dating yields a very precise chronological stamp. Radioactive isotopes trapped within the crystalline structure of the ash decay at an unwavering, steady rate, allowing scientists to pinpoint the exact moment these rocks cooled 74 millennia ago. Matching this radiometric date with a timeline derived from human DNA creates one of the most breathtaking intersections in modern science. That meticulously calculated date of 74,000 years ago perfectly mirrors the profound genomic anomaly discovered by evolutionary biologists. Our ancestors did not undergo a spontaneous biological constriction in a vacuum. They were directly caught in the severe fallout of the Earth, rapidly exhaling a massive portion of its internal thermal budget. The sudden global cooling triggered by the sunlight-blocking aerosols reshaped the terrestrial biosphere, placing unprecedented stress upon early human populations scattered across the Old World. Picture a colossal hourglass towering in the mind's eye to comprehend the magnitude of this demographic contraction. Within the broad upper chamber rests a vibrant collection of sand grains, representing the rich genetic diversity of the early human population before the eruption. Hundreds of thousands of individuals, carrying a vast array of unique evolutionary lineages and physical adaptations, slowly filtered downward through the passage of time. Abruptly, the glass pinches inward, forming a very narrow neck. This severe restriction embodies the harsh planetary reality following the Sumatran detonation. Millions of distinct grains remain trapped above, their unique genetic contributions halted by the sudden collapse of their local ecosystems. Only a remarkably small number of grains managed to slip through that brutal pinch point, dropping down to form the foundation of the lower chamber. Every single human being walking the earth today descends from those few resilient grains that navigated the narrowest passage of our evolutionary history. Survival through this environmental filter required far more than biological hardiness. When the sky darkened and temperatures plummeted, instinct alone proved insufficient. Large mammals possessing immense physical strength and heavy fur coats perished in staggering numbers, alongside countless other species unable to adapt quickly enough to the shifting climate. Humanity, physically frail and lacking specialized natural defenses, should naturally have joined the vast ranks of the extinct. Instead of succumbing to the cold and the dark, our lineage executed a masterful display of cognitive supremacy. Enduring a dramatically altered climate demanded an immediate, radical acceleration of human intellect. We utilized the most powerful evolutionary advantage ever developed on this planet: the highly complex, interconnected frontal cortex. Early humans observed the failing plant life and shifting migratory patterns of surviving animals, calculating entirely new survival strategies. They fundamentally reinvented their relationship with the natural world, engineering specialized tools to hunt unfamiliar prey and expanding their diets to include resilient marine resources along the coastlines. Fire transitioned from a convenient luxury into a life-sustaining necessity. Mastering the manipulation of flame allowed these scattered bands to artificially replicate the lost warmth of the sun, unlocking the crucial calories hidden within tough roots and dense meats. More importantly, the severe external pressure forged an unbreakable necessity for social cohesion. Isolated families realized that surviving a deeply impoverished landscape required combining their knowledge and sharing their deeply limited resources. Complex spoken language likely experienced a dramatic evolutionary leap during this period, serving as the ultimate tool for transmitting vital survival data across generations. Elders transformed into living libraries, verbally coding the geography of hidden water sources and the behavioral patterns of prey into stories that sustained their communities through the longest, darkest winters. We did not merely scrape through this geological crucible, we thought our way out of it. The population bottleneck stripped away our genetic diversity, but concentrated our cognitive brilliance. Those who navigated the harsh new reality successfully passed on genes optimized for extraordinary adaptability, deep cooperative behavior, and relentless problem-solving. Every technological marvel we build today, from the orbital satellites mapping the deep Earth to the mass spectrometers reading the isotopic echoes of ancient ash, originates directly from the intellectual capacity forged in the immediate aftermath of that supereruption. Bearing this history completely reframes how we view our own molecular structure. Human DNA acts as a living, breathing archive of planetary events. You carry the permanent, undeniable signature of the Toba catastrophe within every cell of your body. Our deeply homogeneous genetic code stands not as a monument to our fragility, but as the ultimate, triumphant testament to our endurance. It serves as a unifying biological truth, proving that despite our superficial differences, we are all the direct descendants of a remarkably tight-knit group of survivors who collectively outsmarted a dying world. The monumental scale of this prehistoric event inevitably draws our gaze back toward the present. Understanding that continental crust can and will fracture under the thermodynamic pressure of the mantle prevents us from viewing the Earth with dangerous complacency. The same mechanical forces that ruptured the Indonesian archipelago continue to operate in absolute darkness beneath heavily populated landmasses today. Tracing the chemical fingerprints of past eruptions naturally leads researchers to monitor the active, swelling reservoirs currently storing unimaginable amounts of liquid fire. The anatomy of a potential modern climax is mapped by applying forensic knowledge gathered from ancient ashbeds directly to the subtle, ongoing deformations happening beneath contemporary forests. We must transition from archaeological retrospection to forward-looking physics, meticulously calculating what happens when the tensile strength of the North American tectonic plate finally encounters a mathematical limit it can no longer sustain. Reaching that limit initiates a sequence of events governed by the strict, unyielding laws of thermodynamics. Directly below the Wyoming landscape, an active reservoir of viscous rhyolitic magma presses upward against its rocky confinement. To accurately visualize this impending mechanical threshold, one must imagine a colossal pressure cooker operating deep underground. Everyday culinary equipment functions by trapping thermal energy inside a rigid metal chamber, relying upon a weighted metallic lid to prevent pressurized steam from escaping into the surrounding air. Tectonic architecture behaves similarly, albeit on a spectacularly amplified scale. Unfathomable layers of dense granite and basalt provide the essential weighted lid over the Yellowstone hotspot. Millions of tons of solid bedrock press downward, effectively sealing the incredibly volatile system. Heat continuously arrives from the mantle below, transferring extreme energy into the viscous liquid and demanding physical space to expand. Maintaining equilibrium within this closed system requires the overlying crust to absorb immense mechanical strain. Geological models programmed into our most advanced supercomputers reveal exactly how this subterranean containment vessel handles the ascending thermal stress. Crystalline structures within the bedrock stretch and warp, accommodating the swelling volume of the magma chamber slowly. Eventually, the upward force generated by the trapped, expanding gases outmatches the tensile strength holding the continental plate together. Mathematical certainty dictates that the rock must eventually fail. Microfractures propagate rapidly through the lowest layers of the lithosphere, linking together in the dark to form massive vertical fissures. Severing these molecular bonds compromises the structural integrity of the entire region, turning a stable landscape into a rapidly failing containment system. Fracturing the geological lid triggers a sudden shift in internal pressure. Fissures racing toward the surface instantly connect the highly pressurized magma chamber directly to the open atmosphere. Encountering this sudden path of least resistance, the trapped volatile gases exsolve violently from the molten rock. We previously mapped how rapid depressurization acts upon liquid fire, but a vastly expanded mental framework is required to scale this chemical reaction up to a continental level. The entire liquid reservoir shreds itself from the inside out. Expanding gas bubbles tear the viscous magma apart, transforming a sluggish, subterranean paste into an accelerated mixture of vaporized gas and razor-sharp shards of pulverized earth. As it escapes the breached containment vessel, this searing column of matter accelerates to supersonic velocities. It punches a massive thermal corridor straight through the troposphere, driven by unimaginable kinetic force. Volcanologists calculating the projected output of a modern Wyoming climax measure the ejected volume strictly in thousands of cubic kilometers. Visualizing such an astronomical quantity of material defies everyday human experience. Picture an unbroken wall of solid stone, miles high, and stretching from New York to Los Angeles, suddenly pulverized into microscopic fragments and launched simultaneously into the upper atmosphere. Evacuating this immense volume of material from the Earth's crust leaves a monumental void below, causing the shattered remnants of the overlying landscape to collapse inward and redefine the regional topography. Reaching the high stratosphere, the ascending column of pulverized rock encounters the fast-moving currents of the global jet stream. High-altitude winds intercept the microscopic debris, transforming a localized structural failure into a rapidly expanding continental phenomenon. Meteorologists utilize complex aerodynamic algorithms to map the trajectory of this airborne material. Supercomputers calculate exactly how varying particulate sizes behave when suspended inside the upper atmosphere. Heavier, denser fragments of pumice and rock rain down relatively close to the evacuation zone, burying the immediate surrounding states under dozens of meters of material. Microscopic silica shards, however, ride the powerful atmospheric currents eastward, expanding into a massive, darkening cloud that systematically blocks the sun across the vast expanse of North America. Depositing this staggering volume of particulate matter radically reconfigures the terrestrial environment. Mathematical fluid dynamics models predict a profound geographical transformation occurring within mere hours. Vast agricultural plains stretching across the American Midwest gradually disappear beneath an ever-deepening blanket of heavy, grey dust. Crucially, this falling material shares no physical characteristics with the soft, organic ash produced by burning wood. Volcanic tephra consists of extremely abrasive, microscopic glass crystals and shattered minerals, falling relentlessly from the obscured sky. This dense particulate naturally fills in deep ravines, severely alters regional elevations, and buries established topographical markers. The sheer weight of the accumulating silica strains, natural structures, and human engineering alike, reshaping the continent not through fiery destruction, but through a silent, relentless burial. Hydrological networks spread across the hemisphere face a sudden influx of solid mass. Flowing waterways like the Missouri and Mississippi rivers, traditionally acting as the primary drainage arteries for the continent, encounter a massive physical blockade. Billions of tons of falling silica choke these vital channels, turning swift, fluid currents into sluggish, cement-like flows. Water physics dictates an undeniable rule: displaced liquid must constantly seek new avenues of least resistance. Blocked by mountains of accumulating tephra, major rivers simply overtop their ancient banks. They actively carve entirely new channels across the altered plains, flooding adjacent valleys and abandoning their historic routes. Observing this process through the lens of geological fluid dynamics reveals a hemisphere being abruptly, yet systematically, redrawn in a matter of days. Ecosystems bound to these waterways experience a rapid transformation. Lakes fill with heavy sediment, displacing vast quantities of fresh water onto the surrounding terrain. Riparian habitats, normally sustained by predictable seasonal flooding, find themselves buried under meters of abrasive stone. Entire watersheds reorganize themselves, responding to the newly imposed topography. Engineers studying these probable outcomes do not view the shifting rivers as malicious acts of nature, but as predictable responses to a massive redistribution of planetary mass. We map these projected flood zones using advanced satellite telemetry, digitally simulating where the displaced water will carve its fresh path through the deposited ash. Confronting such an overwhelming planetary mechanism might naturally invite primal terror, yet our collective response remains rooted in analytical triumph. Humanity does not cower blindly beneath the shadow of a hypothetical eruption. We actively quantify the extreme parameters of the unknown. Fluid dynamicists feed millions of variables into massive parallel computing clusters, precisely predicting the altered flow rates of debris-choked rivers. Atmospheric chemists meticulously model the complex chemical interactions occurring within the expanding high-altitude ash cloud. Geologists continuously refine their seismic tomography, vigilantly monitoring the exact volume and temperature of the molten rock slumbering beneath the national park. Every single data point collected, every complex equation solved, empowers our species to anticipate and comprehend the raw mechanics governing our dynamic world. This profound dedication to scientific measurement elevates human intellect above the chaotic forces of nature. We construct digital twins of our planet, running endless simulations to watch continents transform safely within the confines of our laboratories. By dissecting the precise physics of a continental caldera collapse, we strip away the ancient myths and terrifying folklore that once surrounded geological phenomena. We recognize the breaking crust and the falling ash merely as the Earth executing a necessary thermodynamic transfer. It stands as a majestic, entirely neutral process of planetary metabolism. Our unique ability to stand before such colossal natural machinery, armed with calibrated instruments and an insatiable desire to understand, represents the pinnacle of evolutionary achievement. The immediate kinetic violence experienced during the eruption and the subsequent geographical burial only represent the initial phases of this transformative event. While the heavier rock fragments rapidly settle across the continent, severely altering the terrestrial surface, a completely different chemical process initiates miles above our heads. Suspended high above the settling dust, the finest microscopic aerosols remain trapped within the stratosphere. Thrust beyond the reach of rain clouds and normal weather patterns, these airborne molecules begin to execute a profoundly different set of physical laws. The full anatomical climax of Yellowstone demands that we turn our analytical gaze upward, tracking how this high-altitude debris begins to fundamentally rewrite the chemistry of the sky. Ascending far beyond the turbulent weather systems governing our daily lives, the invisible gaseous payload of the eruption enters a realm of absolute stillness. To accurately visualize this atmospheric transformation, imagine standing inside a massive, engineered botanical greenhouse. Architects specifically designed these curved glass roofs to capture and amplify the radiant warmth of the sun. Photons stream freely through the transparent panes, striking the dark soil below and transforming into localized heat that actively sustains a thriving, deeply complex, enclosed ecosystem. Now, picture a technician deliberately spraying a microscopic, uniform layer of translucent white paint across that outer canopy. Light still manages to penetrate the structure, illuminating the interior with a soft, diffused glow, yet the crucial thermal energy is systematically deflected outward. The interior remains bright enough to navigate, but the essential warmth previously fueling the vast botanical life vanishes, bouncing harmlessly off the altered exterior back into the open environment. Our planet operates on a similar thermodynamic principle, utilizing its protective atmosphere as a sophisticated thermal trap. Incoming solar radiation naturally warms the terrestrial surface, granting the energetic requirements needed for dense forests, expansive grasslands, and deep oceans to flourish across diverse latitudes. A colossal caldera collapse fundamentally modifies the physical properties of the upper atmosphere. While heavy, silicate particulate plummets quickly back to the ground, reshaping the topography, millions of tons of invisible sulfur dioxide gas actively punch their way upward, reaching altitudes exceeding 20 kilometers. These highly volatile molecules enter the stratosphere, a stable, stratified layer nearly devoid of the cleansing rainstorms that typically wash impurities out of the lower troposphere. Suspended securely within this high-altitude sanctuary, the sulfur dioxide initiates a breathtaking chemical cascade. Intense, unfiltered ultraviolet radiation from the sun constantly bombards these isolated gas molecules, providing the immense raw energy required to sever their stable atomic bonds. Free oxygen atoms bond with the sulfur, generating sulfur trioxide, a highly reactive compound that eagerly seeks out the deeply scarce water vapor drifting through the thin stratospheric air. Merging seamlessly with these scattered water molecules, the gas undergoes a remarkable phase change. It actively condenses into highly concentrated, microscopic droplets of sulfuric acid. Billions upon billions of these tiny aerosols bloom simultaneously across the upper atmosphere, caught in the rapid stratospheric winds. Pushed relentlessly by these high-altitude currents, the acidic droplets form a dense, globe-spanning haze that envelops the planet in a high-altitude veil. Measuring merely fractions of a micrometer in diameter, these newly forged droplets possess a unique optical property capable of rewriting the global climate. They function effectively as trillions of perfectly distributed, microscopic mirrors floating at the very edge of space. Climatologists precisely calculate the albedo, or reflective capacity, of this expanding aerosol layer, discovering a highly efficient deflection mechanism operating on a planetary scale. As raw sunlight races toward the Earth at absolute velocity, encountering this artificial stratospheric barrier forces a profound physical interaction. A massive percentage of the incoming photons scatter upon impact. Radiant energy that would traditionally penetrate the troposphere to warm the continents gets actively redirected. It bounces off the sulfuric haze, streaming instantly back out into the freezing void of the solar system. Deflecting this colossal volume of solar energy induces a deeply systemic thermal recalculation across the entire globe. Down on the surface, the visual impact appears deceptively subtle during the initial phases. Skies do not turn pitch black, nor does a terrifying darkness instantly consume the continents. Instead, the ambient daylight assumes a highly peculiar, milky quality. Radiant, intensely colored sunsets dominate the horizon, born from the heavily scattered particulate matter bending the light into vivid bands of crimson and violet. Yet, despite the persistent illumination, the fundamental heat transfer sustaining the biosphere dramatically ceases. Average global temperatures plummet rapidly, responding strictly to the undeniable mathematical deficit of incoming solar radiation. Meteorologists tracking this precise phenomenon describe a sudden, inescapable shift where the familiar, comforting cycle of the seasons breaks down entirely. Summer, defined biologically and meteorologically by its abundant warmth and intense solar exposure, is systematically erased from the calendar. Experiencing this immense planetary cooling involves witnessing a slow, highly mechanical cessation of normal climatic behavior. Frost begins to materialize quietly on morning grass during months traditionally associated with sweltering, humid heat. Snowfalls arrive unseasonably early across temperate zones and resolutely refuse to melt, slowly accumulating into highly durable white blankets. Laying down these massive expanses of pristine snow further increases the surface albedo of the planet, establishing a deeply efficient feedback loop that actively reflects even more precious sunlight back into space. Oceans, acting normally as immense thermal batteries regulating the global climate, gradually bleed their stored warmth into the rapidly chilling air above. Ice sheets naturally expand their territories outward from the frozen poles, creeping methodically toward the equator as the Earth transitions steadily into a profound, quiet freeze. Nature executes this massive shift without relying on explosive violence or deafening noise. It represents a purely silent, mathematically precise adjustment to a newly established thermodynamic reality. The roaring energy of the original volcanic detonation gives way completely to the absolute stillness of a dramatically cooled world. Landscapes that previously echoed with the vibrant sounds of thriving ecosystems grow remarkably quiet under the deepening cold. Lakes lock tightly under thick sheets of transparent ice. Rivers drastically slow their chaotic flows, and the relentless atmospheric heat engine driving powerful cyclonic storms effectively loses its primary fuel source. We are observing the planet shifting gears, lowering its vast internal temperature to accommodate the newly constructed chemical mirror suspended high above. This global transition relies heavily upon the analytical capabilities of modern science. We do not merely guess at the extent of this atmospheric alteration, nor do we cower in ignorance beneath the hazy sky. Brilliant teams of atmospheric physicists launch high-altitude weather balloons equipped with exquisitely calibrated optical spectrometers, directly measuring the density and chemical composition of the aerosol layer miles above our heads. Satellites orbiting in the cold of space turn their delicate sensors downward, mapping the thickness of the sulfuric cloud cover and tracking its microscopic movements across the hemisphere. Supercomputers running staggeringly complex global circulation models seamlessly ingest thousands of diverse variables, accurately predicting exactly how much the ambient temperature will drop across specific geographical regions. By completely understanding the intricate molecular interactions occurring in the stratosphere, our species successfully quantifies a climate-altering mechanism capable of plunging the entire world into a deep slumber. Calculating the exact lifespan of these suspended aerosols reveals another predictable timeline. Physics dictates that gravity must eventually reclaim even the lightest particulate matter. Over the course of several years, the microscopic droplets slowly agglomerate, growing just heavy enough to sink back into the turbulent lower atmosphere. Encountering the dense, moisture-rich storm systems of the troposphere, the sulfuric acid finally washes safely back to the Earth's surface in gentle rains, gradually clearing the high-altitude mirrors and allowing the vibrant warmth of the sun to return. Anticipating this inevitable clearing showcases the majestic foresight of human intellect, proving we can plot the duration of a global freeze long before the first snow begins to melt. Gazing upward at a temporarily altered sky, an educated mind perceives an exquisite demonstration of planetary mechanics rather than an arbitrary punishment. Our ancestors who endured the prehistoric Sumatran eruption felt this exact chilling wind and watched their familiar summers vanish. Yet they adapted, innovated, and ultimately thrived. Modern humanity stands far better prepared, armed with a deeply granular understanding of the laws governing light, chemistry, and atmospheric dynamics. We possess the unique intellectual capacity to map the precise trajectory of every reflected photon and calculate the exact cooling rate of the vast global oceans. Mastering this profound knowledge transforms a massive climatic shift into a mapped thermodynamic equation, we stand confidently as the brilliant observers of our universe, capable of measuring the exact weight of a shadow cast across the globe. Understanding the physics of this deflected sunlight establishes the perfect foundation for examining the ultimate terrestrial impact. The atmosphere has flawlessly executed its chemical transformation, and the mathematical reality of a drastically cooled planet has firmly taken hold. To trace the consequences of this dimmed sun, we must lower our calibrated instruments from the high stratosphere back down to the terrestrial surface. Past the initial drop in temperature, we must observe how a complex living planet alters its intricate biological metabolism when abruptly deprived of its primary power source. Descended from the veiled stratosphere, the diminished light encounters an infinitely complex biological engine covering the terrestrial surface. Billions of distinct organisms operate precisely like interconnected gears within a planetary mechanism, all reliant upon a single external power source. When that radiant energy fades, the biological machinery does not violently detonate or crash in a moment of cinematic chaos. Instead, the entire system begins a slow, highly methodical deceleration. Botanists and quantum biologists utilize instrumentation to map the precise pathways a photon takes when it strikes a leaf. Modern science details perfectly how chloroplasts function as microscopic solar panels, catching incoming light to split water molecules and forge energy-dense carbohydrates. Within a sun-dimmed world, this chemical reaction encounters a major physical barrier. Photons arrive far too sparsely to sustain the massive energetic requirements of global vegetation. Chlorophyll molecules sit idle, waiting for a radiant charge that barely arrives. Reacting to this severe energy deficit, vegetation executes a highly calculated mechanical shutdown. Trees halt new growth entirely, shed their foliage, and retreat into a profound dormant state, actively conserving their remaining caloric reserves to outlast the spreading cold. Marine ecologists track a remarkably similar cessation, rippling simultaneously through the vast global waterways. Microscopic phytoplankton act as the primary biological dynamos for the entire aquatic realm, generating more than half of the molecular oxygen we breathe, while firmly anchoring the massive marine food web. Drifting near the surface, these highly efficient organisms require abundant direct sunlight to drive their internal chemistry. Lowering the ambient light levels forces their microscopic factories to stall quickly. Satellites equipped with highly sensitive spectrometers routinely monitor the vivid green blooms of these microscopic producers across modern oceans, allowing our scientists to quantify their daily carbohydrate output. Applying these precise metrics to a volcanic winter scenario reveals a staggering mathematical decline. As the high-altitude haze filters out the crucial wavelengths of light, phytoplankton simply stop multiplying. Their populations dwindle mechanically, effectively cutting the primary transmission line of energy that powers the immense aquatic depths. Depriving the primary producers of their required solar fuel initiates a perfectly sequential chain reaction across every continent and ocean basin. Biologists categorize ecosystems into strictly defined trophic levels, conceptualizing the transfer of energy from plants to herbivores and eventually to apex predators as a highly rigid thermodynamic ladder. Ascending each rung requires a continuous influx of calories from the level directly below. Without the constant generation of new plant matter, grazing animals find themselves consuming a rapidly depleting resource. Grazers do not vanish overnight in a dramatic cataclysm. Rather, they experience a gradual, clear mathematical deficit. Caloric expenditure required to forage in a cooling, darkening landscape exceeds the energy extracted from the remaining nutrient-poor vegetation. Mammals and insects alike exhaust their internal fat stores rapidly, slowing their metabolisms until their biological engines simply lack the essential fuel to continue turning. Mastering the underlying mathematics of this trophic cascade stands as a towering monument to human analytical capability. We do not rely on vague assumptions to understand ecological shifts. Ecologists build massively intricate digital models, simulating the energetic requirements of tens of thousands of interacting species. By programming the strict laws of thermodynamics into these advanced simulations, we can effectively watch a virtual biosphere react to a sudden solar deficit. Supercomputers calculate the exact threshold where a declining insect population triggers a critical food shortage for migratory birds. Researchers map the invisible, deeply complex energetic threads binding an entire forest together, proving that biology operates fundamentally as a vast, highly sensitive thermodynamic equation perfectly bound by physical laws. Predatory species occupying the uppermost tiers of this biological hierarchy inevitably face the most severe consequences of the winding down. Apex carnivores require immense territories and abundant prey populations to sustain their highly demanding physical architectures. As the herbivores thin out mechanically, the energy available to the hunters dwindles correspondingly. Packs of wolves or solitary feline predators must expend increasingly larger amounts of kinetic energy to secure a successful kill, tipping their internal biological ledgers further into the negative. Nature handles this imbalance without a shred of malice. The system simply recalibrates its population numbers to match the newly restricted energy budget provided by the dimmed sun. Larger, more energetically expensive organisms naturally filter out of the equation, leaving only those exceptionally capable of surviving on minimal caloric intake. Fungi and decomposing bacteria, however, experience an entirely different reality during this widespread cessation. Scavenging organisms function as the crucial recycling mechanism within the planetary engine, programmed specifically to reclaim complex organic molecules left behind by failing flora and fauna. While the photosynthetic world stalls, the deeply hidden realm of the decomposers momentarily accelerates, mycelial networks sprawling endlessly beneath the topsoil feast upon the sudden abundance of fallen timber and dormant organic matter. They work tirelessly in the dark, utilizing highly specialized enzymes to break down rigid cellulose and tough proteins. Tracking these subterranean processes reveals an exquisite balance inherent within the natural order. Nothing goes to waste in a closed thermodynamic system. Energy merely changes form, transferring quietly from a towering pine tree down into a microscopic spore waiting patiently beneath the frost. The extraction of physical proof for this prehistoric ecological deceleration requires sophisticated forensic paleontology. Scientists excavating layers of sediment corresponding to the 7-4 millennia mark do not merely look for fossilized bones scattered in the dirt. They analyze the precise elemental isotopes locked permanently within the enamel of ancient animal teeth. Mass spectrometers decode the exact ratios of carbon and oxygen embedded inside these incredibly durable biological records. Herbivores grazing on lush, sun-drenched grasses absorb a distinctly different isotopic signature compared to animals forced to consume sparse, highly stressed vegetation. Reading these microscopic chemical diaries reveals a stark, clear dietary shift perfectly synchronized with the geological fallout. We mathematically trace the exact moment the terrestrial menu changed, observing the severe nutritional stress permanently stamped into the physical remains of the surviving wildlife. Studying the physics governing cold-blooded versus warm-blooded survival further highlights the strictly mechanical nature of this planetary event. Cold-blooded reptiles and amphibians, reliant upon direct ambient heat to regulate their internal metabolisms, faced a sudden operational failure. Lacking the internal furnaces utilized by mammals, countless ectothermic species simply locked into a state of deep torpor from which they never awoke. Conversely, endothermic birds and mammals possessed the biological machinery to generate their own heat, provided they could steadily fuel their internal fires with highly caloric food. Navigating this brutal thermodynamic gauntlet effectively filtered the global biosphere, selecting strictly for physiological efficiency and behavioral adaptability. Evolution utilized the prolonged freeze to audit the biological ledger, stripping away highly specialized, energetically expensive designs in favor of rugged, highly versatile organisms capable of processing marginal resources. Navigating this profoundly altered biological landscape demanded unparalleled ingenuity from our ancient ancestors. Early hominids trapped within the Sumatran volcanic winter watched their familiar hunting grounds transform radically. Herds of large game migrated unpredictably or disappeared entirely, while traditionally reliable foraging sites yielded nothing but withered stalks. Enduring this severe caloric deficit forced a massive, rapid cognitive leap. Human minds actively bypassed the collapsing primary food web by identifying entirely new energetic pathways. Coastal tribes realized that marine ecosystems, while significantly impacted, retained crucial localized pockets of high-calorie resources like mollusks and deep-water fish. Inland populations utilized sharp sticks and deep environmental knowledge to unearth buried tubers, actively hacking the biological engine to extract the final hidden reservoirs of stored solar energy. We survived precisely because our intellect allowed us to dynamically rewrite our dietary strategies faster than the climate could freeze us out. Today, our species commands a far greater understanding of these biological limits. We actively monitor global crop yields using orbital sensors capable of measuring the exact chlorophyll fluorescence emitted by massive agricultural grids. Agronomists sequence the genomes of highly resilient desert plants, isolating the specific DNA sequences responsible for extreme drought and cold tolerance. Armed with this molecular knowledge, botanists engineer advanced crop varieties specifically designed to thrive under highly restricted solar conditions. We deliberately construct massive, artificially illuminated indoor farming complexes, proving unequivocally that humanity can synthesize its own primary production independent of the fluctuating skies. Should another massive caldera breach its containment, we possess the technological capacity to artificially sustain the fundamental biological engine, insulating our populations from the harshest effects of a dimmed sun. Witnessing this biological auditing process from a scientific perspective instills a deep sense of awe rather than despair. The biosphere simply executed a calculated response to a sudden restriction in its primary power supply. Forests stood entirely silent, their metabolic processes paused in a magnificent display of organic conservation. Vast plains remained utterly still beneath the heavy stratospheric haze, hosting only the most resilient, highly resourceful scavengers. Nature demonstrated an unmatched capacity for endurance, pulling its vibrant energy inward and locking it safely beneath the frost line. Life did not surrender to the cold. It merely changed its operational frequency, dropping into a very low-power state to wait out the long, artificially induced winter. This quiet, methodical conservation of biological energy prompts a much larger realization. Focusing exclusively upon the chilling aftermath generated by a massive atmospheric aerosol injection captures only a tiny, localized fraction of a much grander geological narrative. Up to this point, we have heavily scrutinized the severe biological interruptions caused by liquid rock breaching the continental crust. We mapped the failing sunlight, the plunging temperatures, and the meticulously calculated slowing of the global food web. Exploring these disruptive phenomena remains a crucial step in understanding planetary mechanics. Yet, it inherently paints the subterranean forces as agents of pure cessation. We must invert this analytical perspective to grasp the majesty of our living world. This intellectual pivot requires stepping away from fragile ecosystems, clinging to the modern crust, and directing our highly calibrated instruments backward toward an era when the globe was nothing more than a barren, hostile sphere of cooling rock. Rewinding the planetary clock far beyond the origins of biological life brings us directly into the chaotic infancy of the Hadean Eon. 4.5 billion years ago, our newly coalesced world bore absolutely no resemblance to the vibrant blue biosphere we currently inhabit. Orbiting a young, highly active star, the early globe existed simply as an incredibly hostile sphere of partially molten rock subjected to continuous celestial bombardment. No protective atmosphere filtered the harsh ultraviolet radiation pouring out from the sun, and no vast oceans existed to moderate the extreme surface temperatures. Vast expanses of raw, exposed magma dominated the topography, radiating immense quantities of primordial heat directly into the freezing vacuum of space. Visualizing this desolate landscape requires stripping away every familiar comfort of our modern environment, leaving behind only the fundamental physical elements violently colliding in the dark. It took an engineering mechanism of staggering proportions to transform this barren celestial body into a habitable oasis. Deep within the churning, heated mantle, microscopic droplets of water and essential chemical volatiles remain tightly bound within the crystalline structure of dense minerals. Locked hundreds of miles beneath the hardening crust, these crucial biological building blocks possessed no natural method to reach the surface. Releasing them demanded an aggressive, energetic transport system capable of breaching the solidifying lithosphere. Extreme volcanism emerged as the ultimate architectural force, stepping in to construct the fundamental infrastructure of our entire world. Towering plumes of incandescent rock relentlessly punctured the primordial crust, initiating a planetary-scale process that geochemists classify as volcanic outgassing. Erupting across every hemisphere, these ancient fissures and towering calderas functioned as massive chemical exhalers. Boiling magma, reaching the absolute zero of the surface, instantly depressurized, releasing trapped payloads of nitrogen, carbon dioxide, methane, and vital water vapor. Billions of tons of these invisible gases poured steadily upward from the deep interior, captured by the gravitational pull of the planet to form our very first atmosphere. Without this relentless, fiery expulsion, the Earth would have permanently remained a frozen, airless rock drifting silently through the void. We owe the very existence of our protective sky strictly to the sustained, overwhelming thermodynamic violence that actively tore the early crust apart. Centuries melted into millennia as the atmospheric pressure thickened and the vast fields of surface magma gradually radiated their thermal energy away. Dropping global temperatures eventually allowed the highly concentrated water vapor suspended in the thick, toxic sky to undergo a magnificent phase change. Microscopic droplets condensed high above the cooling rock, initiating a meteorological event that defies standard human comprehension. Torrential downpours began to fall, inaugurating a continuous, planet-wide deluge that lasted for millions of years. Boiling rains hissed against the searing basalt, flashing instantly back into steam before returning to the sky in a relentless hydrological loop. Gradually, the crust cooled just enough to permit liquid water to pool in the deepest impact craters and vast tectonic depressions. Liquid fire literally gave birth to the global ocean, filling the abyssal plains with the precise chemical solvent necessary to eventually forge complex biological life. Operating as an integrated planetary metabolism, this fiery cycle did not simply switch off once the oceans filled. Maintaining a habitable climate over billions of years requires a highly precise, continuous thermostat, a role fulfilled entirely by the enduring tectonic forces churning beneath our feet. Carbon dioxide exhaled by active volcanoes functions as the crucial thermal blanket, keeping our oceans from freezing solid. Simultaneously, the slow chemical weathering of newly exposed volcanic rock actively draws excess carbon back out of the atmosphere, washing it down into the sea where it ultimately subducts back into the mantle. Geologists recognize this majestic silicate weathering cycle as the ultimate stabilizing equation of the Earth. Volcanism actively inhales and exhales the vital elements of life, continually adjusting the global temperature to prevent the oceans from boiling away or locking permanently into ice. Perceiving this colossal geological machinery through the lens of deep time eradicates the concept of planetary malice. Rupturing continents and massive aerosol injections are not catastrophic anomalies sent to destroy a fragile biosphere. They represent the deeply necessary mathematical redistribution of internal thermal energy, keeping the overall system alive. Our beautiful, flourishing ecosystems merely exist atop this grand thermodynamic conveyor belt, temporarily occupying the quiet intervals between essential planetary exhalations. Every single carbon atom currently structuring your cellular DNA and every drop of water coursing through your bloodstream was systematically dredged from the deep mantle and violently ejected into the sky by an erupting volcano. We are not merely inhabitants standing upon the crust. We are the highly complex, biological manifestation of the very rock and gas forged within the Earth's fiery interior. Recognizing our molecular connection to these subterranean forces elevates the human condition. For countless generations, early hominids could only stare at the rupturing ground in blind terror, fabricating supernatural myths to explain the shifting landscape. Modern humanity has brilliantly transcended that primal fear through the sheer power of rigorous scientific inquiry. Armed with high-resolution mass spectrometers, orbital radar, and quantum computing, we actively map the chemical pathways of our own creation. We isolate microscopic isotopes hidden within ancient zircon crystals, effectively reading the diary of the Hadean Eon to deduce exactly how the first oceans condensed. No other species in the known universe possesses the cognitive brilliance required to look backward across 4.5 billion years and mathematically calculate the exact temperature of its planetary birth. This extraordinary intellectual triumph transforms us from helpless victims of a dynamic Earth into enlightened, conscious observers of the cosmos. We deploy delicate seismic arrays across vast tectonic plates, listening intently to the acoustic waves reverberating through the liquid iron core. Geophysicists sit quietly in softly lit laboratories, watching complex algorithms translate these distant tremors into precise, three-dimensional maps of the deep mantle. We accurately visualize the ascending plumes of superheated rock and calculate the tensile strength of the continental bedrock above them. By meticulously decoding the strict laws of thermodynamics, fluid dynamics, and molecular chemistry, human beings have successfully illuminated the darkest, most inaccessible depths of our world. Returning our focus to the serene, pine-covered wilderness of the modern Wyoming landscape brings this evolutionary journey into sharp, breathtaking focus. Deep below the thriving forests and bubbling geothermal pools, the immense magma chamber continues its slow, methodical expansion. Silicate rock melts, volatile gases accumulate, and the sheer physical pressure pushing against the North American plate climbs steadily upward. Yet, understanding the profound duality of this system completely alters how we stand upon the shifting ground. We do not view the swelling caldera as a malicious weapon waiting to erase our civilization. We recognize it perfectly as the steady heartbeat of a living planet executing its vital thermodynamic obligations. Centuries will continue to pass, and the immense thermal engine operating in the dark will relentlessly push the overlying bedrock closer toward its ultimate mechanical limit. Our species stands vigil above this magnificent architecture, continuously refining our instruments and expanding our mathematical models. We measure the rising terrain slowly, unburdened by irrational panic. Armed with an unprecedented understanding of planetary mechanics, we project our awareness far beyond the fragile constraints of a single biological lifespan. Every microscopic tremor detected by our global networks serves as a beautiful reminder of the forces that constructed our atmosphere, filled our oceans, and ultimately shaped the cognitive brilliance we wield today. Standing safely atop this dynamic, ever-changing crust, humanity celebrates its unique position within the universe. We are the ultimate anomaly, a collection of organized volcanic atoms that somehow learned to build telescopes, sequence DNA, and comprehend the very physics governing its own existence. The liquid fire continues to shift silently beneath the continents, transferring immense energy in a perpetually balanced equation of creation and reformation. As the subterranean pressure builds across the centuries, we listen carefully to the quiet, inevitable ticking of the geological clock. We embrace the majesty of a world that is alive, watching with enduring awe and endless curiosity as the ground gracefully holds its breath.